Yes, my friend, let's go on now with the lossless bit compression. Anyway, now we'll write again. Let's start it. We'll say computers represent all data in binary. So all types of files from text to images, from text to images, right? To videos, I mean, yeah, we know that, right? To videos are are ultimately, or ultimately, ultimate. Anyway, I don't know how to pronounce it. Ultimately, ultimately, sequences of bits. Saying computers represent all data in binary. So all types of files, right? From text to images to videos are ultimately sequences of bits. If you want, I can show you one example. Let's look in my computer. I will show you one detail. Let's look together. Yes, this is my terminal. Let's look. Let's do it. Yep. Now, in this point, I want to do what, Let's come there. Yep. Now, let's go there right here. We have binary here. Have you seen binary? And we have S-bin, I mean super binary. Okay, where is it? Let's look at in user. Maybe 1 minute. User. Let's go there. And yeah, we have S-bin here, super binary. It's just you can, you can configure your binary files. Now all the things in computers representing with the binary numbers. What is this binary numbers? Binary numbers is just bits and bytes. All of them right there, like that. Let's go in binary. What I want to show you, I will show you some detail. Let's say we want to go right mesa overlay or not, like that. Let's go in the yes. Let's say nano or cat yes. Yep. Now, all this, have you seen here? We also seen here, viewing here, run length encoding, or right, I think run length encoding. So here we just representing things. With, if you remember, we did together this work. Where is it? Run length, then before bitmaps. Yeah, and then we have what? Right, compression algorithm. Yeah, in compression algorithm, if you remember, we just converted replacements. Original just thing. We have that, and we have do, and we have those, of like that things. So if you check here, we have do all the time is same. Have you see this detail? Do, and do, right? So just we are taking replacements things in the one character or in the one thing to represent all the time and with the same way. This is some example for it. Have you see this things just for what for what we doing that, for compressing files in here. Okay, yeah, let's go up this, all of them. Have you seen? Oh, it's just compressing the files. Let's go down. Just this is some details, and let's go on again. Okay, sequences of bits. We told it, then start to write again. Where is my place? Right here. Regardless 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 of whether the bits of whether the bits whether the bits represent a document represent a document document or a GIF or a GIF. Computers computers can use a bit can use a bit compression technique technique call it. Yes, this is important point. Are you ready? Hoofman coding. Right. Let's tag Hoofman encoding into this color. Yep. Hoofman coding. Now, what is our way to explain it? Regardless of whether the bits represent a document or a GIF, I mean, computers can use a bit compression technique called Huffman coding. Now we will compress the words, the things, the letters in the bits. Just think we have lots of A, lots of B in the one sentences or in the one books. We want to tag which one is a replacement too much. We are tagging in the bits. We are representing with the bits. Anyway, let's go and I will explain all this situation the next lecture or next way we can do together. Let's say, let's come down. Yeah. And this point, let's call it to consciously we will continue. We will continue. Hoofman coding algorithm. And then let's tag it in the blue right here, and let's start to write things. I will start in this point. Yes, uh, let's say let's see how it works. Take it there. How it works. How it works with a simple textual with a textual example. With a simple, I forget the simple here. With a simple textual example, right? We can see together. This example language, this example language using uses this only yep uses only four different characters four different characters and yet is incredibly important to us important to us. So I'm saying here it's the language used to represent the language to language used to represent DNA, you know, right? Adenine, guanine, cytosine, valine. So the cytosine. I don't know how to explain it. Anyway, let's come with me. DNA and is is made up made up of sequences of four characters, which is A, adenine, cytosine, I think, guanine, and thymine. Let's come down and say, for example, the 4.6 million characters representing an holy DNA, right? Sequence happens too short too short with within short with sorry with only with. Now I will show you this one is just short. I explain two things. Wait me. Let's come down also. Really, we have little place here. Okay, this point is good. This one is like adenine, guanine, adenine, guanine, cytosine, and thymine, and cytosine, adenine, thymine, and cytosine, thymine. Okay, this is the point. Now let's look what I'm saying here. If we come here, let's tag it little this place, right? It's good. Now let's say sorry, we need to represent. So this is short with, we don't have time to write 4.6 billion, so 6 million. Just made here, the, how many characters is that? 20, 2, 4, 6, 8, 10, is like 13 or something like that. Anyway, so 13, I think, right? Since uh, we need to represent four characters, uh, a computer would typically represent typically typically represent each character using two bits, such as such as right, such as like what? We have four character, and how we can represent it with the bits? Just think 0 0. We can think like that. So 0 0 1. I mean 1. Then we have 2 and we have 3. So let's think like 3. The first one is 0 0. It will be 4. So what I am saying, let's write it down. So I'm just saying here. Let's think this one to maybe this point, and let's come to here and do same things in here. Say character, and let's go here, say binary code. Okay, let's come here and put this information there like that. I think this is not bad too much. What do you think? Yeah, let's bring little back maybe. Yeah, maybe we can go a little more for binary couplets. Okay. Now, let's come here and say character is A, say A, and we are representing it with the bits like 0, 0. Let's come down. So A is we are representing with the 0, 0. Okay. We have cytosine we are going to represent it with 0, 1. So I mean 1, the 1 bit. Okay. And we are coming here. The other one is guanine. And guanine will be like 1, 0, like 2, right? In binary code. And in bit counting, it is just 2 here, because this 0 power of 2 and 1 power of 2 is going all the way like that. And last one is just Timin. Its Timin is representing with the 1, 1. So what is it? It is 3. Okay, I think you got what I did here, right? But if you want, let's put the space between them to make them clear. Okay, this is the K here. Let's also take this as maybe can be here. Radius is good. So let's write here what I'm saying. The 13 characters above would would be written using using 26 bits 26 bits bits as allow us allows yeah notice is that we don't don't that we don't need gaps between the codes between the codes, right? We don't have any space, so empty interval, I mean codes for each bits no well, each bits, not bits. So the 13 characters above would be written using 26 bits. Why? Because if we count it, the 13 number, just think what it will be then. It is will be like 4 power of 2 will be 16. 16 plus 8, it will be 24. And 24 plus 4, 28. And 28 plus 2, and it will be go like 31. Let's we are thinking about 13, so it's not 16. 13 will represent there just 26 bits. Okay, it is the way to solve this. This is in binary numbers. Okay, so it will go all the way like that. It will be 26 bits. Do you know how to write 26 bits? Let's try it together. Let's say we have 16. One put 16 there, and we can put there also that's 16 plus 8. It will be 24, right? And then what we need? We need 8, then we don't need 4. 4 will be more. Let's put 0. And 2 can be good, of course. So let's say 2, because it will be solution. And for the 1, it will be 0. this is that. So this is the key point here, okay? So we can represent it with the just think 0. It will be 1, then it will be 2. 2 plus 8 is 10, and we have 16. It will be 26. We can represent, I mean, 13 characters with this, okay? This is some practice for you for the future. Maybe you will try something there. Anyway, but the point here, the thing little different. This is not will be like with this bits. I mean, look at here. These all bits will come next to next. I mean, the first one is just think which first one is so A. Then we have G, we have C, we have T. Then we have to write here like what, like that. We have to write 0 0 A. Then we have G. G will be what, 10. Then this one, so right. Then what we have, then we have stozen. Stozen will be 0 1, right? And what we have later, timin, it will be what, 10, no, 11. Then all the time we have 4 timin, so it will be 11, 11, and 11. And again we have cytosine. Cytosine will be 0 1. And we have adenine again. Uh, it will be 0 0. Then we have again thymine. It will be 11. 11 again thymine. And cytosine. It will be 0 1. And last one is again thymine. It will be 11. Now you see uh, the thymine is recurring too much and all the time recurring. Look at here. 1, 2, 3, 4, I think, right? 1, 2, 3, 4, 5, 6. And really it's recurring too much. I think 7 times occurs. So let's solve this problem, how we can compress it with the Huffman coding algorithm, I mean. Okay, let's come here and say, let's take it a little down. Let's bring it down. Yeah. Let's say, but we can do better than this, but we can do better than this. Yes, we can represent again them with something, and it will be easy to do these things. We can do better than this. So, in the short sample text above, in the in the short sample text above, oh, the letter T is more common is more common than is more I told you is more to common than the other letters. Yes, so let's say T occurs 7 times. T occurs 7 times. C is C 3 times, and I mean twice, and G is just once, right? So, did you understand what we did here? The T and C is recurring more than A and G. Okay, so we need to represent them with the short way which one is recurring too much, then really we will compress our sequences of bits. I mean, our sequences of DNA, and we can compress in the one place in the uh, lossless data. I mean, we don't will lose there anything. Okay. Then let's say if 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 we give give a shorter code, if we give a shorter code to t, then with using less space 54%. Yes, of the time of the time. So let's say 7 out of 13 characters. Using less space, it's 50, where is it? 54 of the, it's wrong, of the, right. 7 out of 13 characters. So let's do it. So just we can represent with the 7, not with the 13. It will help us. Let's close it and say, for example, we could use the codes. We could use the codes here. Let's come down. Now here, what I want to do, let's say character again. Let's say binary code. Let's do again this line below them. This is amazing. Let's come down and really just we need to do something here. Again, A, now this is the key here for use Huffman coding. This is important. Let's join in this point and solve together. Now, if you understand this concept here, it will help you too much in the future too for understand concept combine of these things. We will represent A with the what, with the 0 1 0 0 1 0. Why? Because A is just one time recurring term, right? Just check it. Where is A? Yeah, A. Oh, sorry, twice. So this is just 2 times recurring in 13. Okay, this is some example for you. Then, which one we have? Cytosine. The cytosine normally, but also I want to show with you, the first we represent A with the 2 0. But now we are representing with the 0 1 0. Maybe you will say, hey, why you are going to put there too much bits like that with the 3 piece of plays? Just don't worry, you will understand because just it's recurring 2 times, twice. Let's look for C. We will represent C with the 2 0, which is before we put for the A. Now it will be 0 0 because C is recurring 3 times. This is more than 1 bits. So this is more than A. Okay, let's come down, explain the situation again and again. And then let's put it little right to this place. Right, it is good. Yep. Maybe, right, yeah. Don't know why it's staying like that. So it there like that. Okay, now we have what? Guanine. It's guanine. It's recurring how many times? It's just once. Once, then we're just going to put there 011. Okay, don't worry about that. You will understand everything step by step. Don't worry about that. Because it's just recurring one time and once. So A is recurring twice. C is more than this two. So which one is recurring more? We are representing them with the small piece of bits. The last one is important one, timing. We are just representing it with the one because the timing is recurring 7 times. Just think, in all of this 6.5 million, this timing is too much recurring there. Just we will represent with the one. Normally, what we did for timing, look, this is three three bits. This is will take lots of bit space. Now just it will be one. It's one. So 2 bits, we just put our pens. We save it. Okay. And just the A will be very little. For that, we can represent with the three piece of place. I mean, it will be 3 bits. You can think like that. It will not make too much problem there. Let's think like that. Let's come down and say, then our 13 characters would be coded as would be coded as like what? Let's think about that. Let's go here. It will be like what? Let's think together. Yeah. Now it will be like we have first A, it will be 010, and then we have G, this 011, and we have C thousand, I mean, right, 00, and then we have Timin 4 times, it's 1 for Timin, right? Only look, before we put 11 for Timin, right? For now, just we are representing, so we are now representing with the 1 only. Yes, now again, yes, and then we have 4 times, I told you, this 1, 2. Just look, we're representing with the 1. We don't writing there 11. 1, Timin, again 1 Timin, and again 1 Timin. And just with 4 bit, with the 4 bit, I mean with this 4 bit, we represent what? We represent Timin, 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 Timin. We just represent 4 times this Timin. Have you seen? We don't write here like normally if we didn't compress it, it will be like that. 1 1 1 1 and 1 1 again. It will represent T T T this. But we just representing with the 1 2 3 4. No, just we save it for more there. I think we can think like that. Anyway, let's come here and say, let's say 1 after A, after no, after not A, after C. Let's say 1 1 1 1. It's for Timin. And again we have cytosine. Cytosine is like 0 0. And we have adenine. It will be again like 0 1 0. And for Timin again 1 1 2 Timin have there. And again 1 cytosine. It will be 0 0. And the last one is will be Timin. So let's look at this is amazing architecture. Before till now, have you seen? This is just amazing, really. We don't need to write lots of bits there to represent this. Maybe you will say why this is not too much good. It is good, believe me. So just look. We just where is it? Right here. Just I will copy it to show it you, which is the differentiation between them. Right. Let's look. Why we need to put there this for more? We don't need to put, right? This is very important. Look, for now, maybe you will say just 4 bit. We save it here. But let's think about let's go to think about 6.5 million sequences of adenine, guanine, and cytosine. Too many things there. It will save lots of space, friend. So it is the key point here. Huffman coding too much. Huffman coding algorithm too much important for that. Let's take it back there, and let's go on. Let's say that's just 22 bits. That's just 22 bits. So 4 less bits than bits. So not nits, bits, less bits than our original encoding. Yep. That may not seem like a lot. That may not seem that may not seem like a lot, like a lot. But I told you, but imagine here in this point, if we use it, and optimization, optimization, yes, optimization, uh, optimization, like like that, that on the entire 4.6 million 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 characters of the DNA. Yes, this is the important point I told you. For now, just this 22 bits. But if you think about 4.6 million, it will be amazing saving there. It will compress lots of there. Okay, let's say again here, Huffman decoding. The important point also decoding. You encoding, you need to decoding it, right? You need to resolution it, resolution it. How you gonna say resolution? So for solve what you did before. Anyway, from decoding, let's put in the blue again. Right, this is the subtopic of this. And let's come down. Let's start to write. You may be scratching your head. You may be, you may, you may be scratching, scratching, right? Scratching your head at the new, your head at the new binary codes. where we're using with all different lengths, with all different lengths. Is it still possible to? Is it still possible? Possible to? Is it still possible to decode it? Decode it reliably, right? Reliably. This is a question. You may be scratching your head at the new binary codes we're using. We're using with all different lengths. Is it still? Yeah, for that I just read back because I know what is turning there. Still possible to decode it reliably. So reliably? Yes, with the right set of codes. Yes, with the right set of codes. Yep. Now let's say here try anyway, let's come down for this and say and try it for yourself. Try it yourself. Yes, put it in the different color like this. Yep. And let's come down here in this point. Yep. Now say decode the following bits. Using to optimize it. Using to optimize it binary codes. Yes. Let's come down. Our key will be here, so our bits will be here, and I will ask you what it is, and you will tell me 1 1 1 0 0 1. And let's come down. Here our thing will be character and will be binary code. Okay, let's come here, this place, and let's say again this will be adenine. Adenine will represent with the 0 1 0 and cytosine. So let's say here cytosine will be, how you remember, 0 0. Let's say uh, the guanine will be 0 1 1, which is less recurring, 0 1 1, and the last one will be thymine. Let's come a little bit down with me. Yeah, here maybe good. This one will be thymine, and let's say this is 1. Let's decode it. Have you see? We have some number here, and if you solve it, you will solve DNA chains, right? Chains is true for chains, I think, right? Let's look at it. I will try to look at chains. I don't know. I will try to look at. Let's give me time. Just I want to be sure about that. Let's say translate. This is something chains. I don't know how to use chains. Yeah, chains, right? Chains is just like right, chains. You will solve DNA chains in this point, but the pronunciation is like what? Chains. Chains is chains. Okay, let's solve it. But now, what I want to do, we have here uh, the answers. Let's come down. Let's come down to this point, okay, and say make some. So make sure you start off the first. You start off the first bit on the left bit on the left and up match up the codes from left to right, from left to right. What DNA string, I mean chains or string do you come up? Do you come up with? Have you solved it? Let's write it. A, B, we have C, we have D. The A will be, let's say, down. Okay. This point, what the fuck? Just come back right here. The A will be here. Timin, guanine, timin, cytosine, and timin. The other one will be timin, cytosine, timin, adenine. Other one will be timin, cytosine, adenine, timin. The last one will be timin, cytosine, timin. Let's check which one is true, which one is false. I will take my pencil, let's take it and come up and let's look. The first one is looking like timin. So let's say the first one is looking like timin. The second one is also looking like timin. The third one is also looking like timin, right? It's three timin we have. And then we have, so let's look, this 3 times is recurring here. You see? So in this point, we have 3 times recurring anyway. Then we have cytosine, I think, because just check it, okay? 0, 0, starting like that. And we know this is cytosine. Let's say this is cytosine. And last one will be again thymine. So what is so we just we were decoded it right now. Let's look which one is true answer. Thymine, cytosine, thymine. So it is thymine, cytosine, thymine, which is this one wrong, this one wrong, which one is this one wrong, and this one is true. So have you seen? We decoded it. This is Huffman calling too much helping us to solve this kind of problems. Let's come down and let's say that's the beauty of Huffman calling. That's the beauty of Huffman coding. So the algorithm gives us algorithm gives us a way to come up, a way to come up with set of binary set of binary set of binary codes a set of binary codes for a given sequence that ensures that ensures right that ensures the data can be the data the data can be reconstructed. I think reconstructed and unambiguously ambiguously and reliably. What it's saying, that's beauty of Huffman coding, of course. The algorithm gives us a way to come up with a set of binary codes for a given sequence of ensures the data can be reconstructed unambiguously and reliably, right? This is the truth. All the time we can encoding and we can decoding when we need. Okay, let's come down and say uses for Huffman coding. Is the key again subtopic it. Let's say the blue is here. And let's come down and let's start to write it here. Let's say many file format utilize some kind of Huffman coding to some kind of Huffman coding algorithm Huffman coding not algorithm sorry Huffman coding to reduce the size of their their size of their file. Fax machines use Huffman coding after using RLA on the black and white runs. So it's saying fax machines use Huffman coding after using RLA run length encoding on the black and white runs. This is also very good. PNG images compress using LZ. Let's have these two guys 77 an algorithm similar to the text compression comparison right compression sorry not comparison compression. Anyway, let's think this is compression. Compression. It's compression. Technique. Technique. We learned combined, combined with Hoffman coding, coding, and the results. Results. Yes. The what is that? Let's look at what is it. Let's close this place. There are you remember the first one? What we did first? We spoke about the same process, but what is different between LZ77, which is so Lempel Z Welch algorithm? It is just the same words, which is doing same operation. So it's like do that, and all the time we have do d. It's the detail there. We're just compressing it with the some character. In this point, Huffman coding doing it with the bits. Okay, this is the important point here. You have to get it. But uh, in Lempel Z-Welch algorithm, we are just doing this operation with the character. So we are just looking for original, then we are converting it with some symbol, which is I showed you. So now if you check, I will show you now details about that. Let's look in my computer this point. Where is that? Now we will see if possible. Yes. Now let's say ls. Let's go to back. Yep. And let's go in binary and come in binary. And let's say cat, and let's go in anything. I don't know which one. Let's say zip. Let's go in zip. Now, have you seen zip? This is what do you know? This is Lempel-Ziv Welch algorithm. It is implementing here. Look, this characters is representing some kind of same things which is recurring all the time. It's just representing with some symbol here. Just look at it. It is something. So it's same thing all the time recurring. Maybe lots of words there. It's just representing with some way. It's just doing that. Now it's saying also we are implementing their Huffman coding after running encoding, which is amazing. Let's think. We put this symbol. So step by step, let's go together. The first one, we implementing this guy. So, I mean, which is meant, it's like his name, I forget it. Yeah, Lempel-Z-Welch algorithm. To compress this same words to the in one character. Then the one character which is recurring too much, we are also implementing add Huffman coding for decoding for the feature. But for the first time we are encoding it. Just think you compressing lots of perfect way these things to make them to save, to store place, to save places, then some use some useful situation. Okay, it is all. Okay, it is. So let's go back there. Yep, let's close it. This is the point. And now we have the we have here uh, practice questions, lossless file compressions for this point. Let's do together with me. Say lossless file comp compression compressions, right? Compressions, and let's say how we can do it. Say practice questions. Uh, but maybe we can do it like what, like just tag it down, something like that. Yes, let's tag all of them, right? Tag them also here, and let's make them different color. Which color? It can be red. Let's do it. Practice question because we know that. And let's come down to here. Start with the first question. The first question say compression algorithms vary in vary in, which is like vary is like I forget. Anyway, I know what is it, but just I forget this short way to write it. Vary in how much how much they can reduce reduce the size of a document. Yeah, it's like varying, right? Document. Which of the following which of the following would likely be would like would likely be the hardest to compress, the hardest to hardest to hardest to compress. Yeah, let's come down. This is A, this is B. Let's do it. This is A, this is B, this is C, and this is D. And let's write it first. The declaration, the declaration of independence, 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 right? The Declaration of Independence. The the lyrics to all of the songs, all of the songs by the Beatles. Let's say by by the Beatles. The one will be a document of randomly generated generated a document of randomly generated letters. So the key point here, just look, And then we have a book of nursery rhymes, rhymes for children, 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 right. No, it's saying compression algorithms vary, and the difference very lot in how much they can reduce the size of document. This is the important. So we have some vary there, various, right? Like various. Anyway, which of the following would likely be too hardest to compress? No, the Declaration of Independence. It will not be hardest. We can do it easily, way. It is just we can compress this and we can implement this Huffman coding there, and it will be easy for our things. So, and then the lyrics to all of the songs by the Beatles. It is also not problem. We can do it in easy way. This one is really not difficult. So when the recurring things we will put in the one bit, or I don't know, we will represent with the some bits, and we will just which one is recurring too much we will represent it with small bits, and which one is recurring more less than other ones we will represent them with a little bit more bits to understand to about comprehension. I mean the other one. So anyway, let's take our pencil the solve this. So this one is which of the following would like be hardest to compress? It will not be to be compressed. Hardest to compress. It will be easy, and this one will be easy. A document of randomly generated letters. Now, this randomly is the key point here. We can't do it with the randomly way because it's generated all the time randomly. Okay, but we are saying how how much we that the can reduce the size of the document, how we can reduce if the things is coming there randomly. It will make us, so it will make the topics too much difficult. So the other ones, look at that, all the time e will be here, or just think like we have do here, and we have some words. Just think if we see again the e, we can represent this 2e with the one thing, with the one bit. But so also let's look at here. We have so I mean e again a, and 4e, and this 5, 6, and 7 we can represent with the just think with the 1, and we can represent which is the 1 d, it's just the, we can say the can be 1 and 0, something like that. Again, you know, it will be for d, it will be for e, which is recurring. But a document of randomly generated letters, this one is crazy here because we don't know when, which will be there, what will be there, because it's randomly generated letters, randomly doing that. Okay, this one is our solution. A book of nursery, it's not birthday, it's nursery rhymes for children. So this is also same concept. It is also not too much difficult. Let's come down. This is also the solution. This one is that. Let's look for the second question. The second question a little bit long than first question, but let's write it in natural languages. In natural languages, languages, there are big differences. There are big differences. There are big differences in what letters are the most, and In what in what letters are the most common common across words? Yeah. In the English language, the letter E is the most common, most common, is the most common occurring, occurring 12, 12.7 uh, percent of the time, of the times. Yeah, it's more of the time. And the letter, and the letter, and the letter Z, I mean, Z is the least common, is the least common, common, is the least common, occurring only, occurring only, occurring only 0.05% time. Yeah, there's some analytic, so there's some counting. I don't know which person is counted. Let's come down. Let's say that's why the Huffman coding, right? Huffman coding algorithm can help. Algorithm, algorithm, algorithm can help us. Help us. Can help to compress natural language, natural language, 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 language documents. Yes, Huffman coding reduces the Huffman coding reduce the amount bits required to represent amount bits to required bit required to represent bits to required to represent data by choosing new bit data by choosing new bit choosing new bit codes for each codes each for each source symbol and choosing shortcuts and choosing shortcuts for the most frequent for the most frequent 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 source symbols. So the here that's why the Huffman coding algorithm can help to compress natural language documents. Huffman coding reduces the amount of bits to require to represent data by choosing new bit codes for each source symbol and choosing shortcuts for the most frequent symbols. So the important point, which is recurring too much, then we need to represent them consciously with the small of bits. I mean, just saying, E is recurring there like uh, thousand times, and we need to represent it with the one. But if the Z, you can think like Z or L recurring there only 50 times, then we need to represent it with the 010, with something like that for comprehension, to solve, to analyze it. Okay, so this is the way to understand this. So you can really realize me. So you can rely me in this point. Really, I want to be, uh, I want to be clear in this point, at that point, because in the future it will help you to understand how to work with the computer programming and this kind of things. It will just give you some general information for computer too in this time. Anyway, let's come down and let's say here's an English word encoded with Hoffman coding. Coding. Yes, let's do it. 010110111110001110. This is that. Now we will decode it together. Let's look details about this point. Let's come down maybe a little bit. Yep. Yeah. Now also we will say here, these are the codes for the ladders in the word in the word uh, in the word in the word subset of the table of the table the table of codes for all the ladders of codes for all. Why it's staying there? Stick it there in the back right here for all the ladders and not ladders, it's ladders and not ladders in the English alphabet. Okay, so let's do it together. Let's say ladder and say bit code. Right, this is fair. And what we need to do, let's do it there, something like that, for be clear. And maybe we can go a little bit more. I will do for you. Down. We can see here, but this is important point here. The ladder here, we will do A. A we will represent with 1110. Don't read bits, okay, like don't count. If you want to do it, but the important point here, representing with the which kind of numbers, so which kind of bits. D will be uh, D will be 11111. I think this is recurring little than others. The other one will be what, it will be E. E, it is just, no, it's, I think, recurring more. The other one will be R, which is 0101. It's recurring less than E, less than, anyway. Let's look R and W. So V, W. can think like that. Yep. Now let's agree. No, it's one, is zero, zero, on one. Yeah, this is comprehension. I told you W is really not too much there. Just think, you can think like E is recurring too much, then D, then W, and R recurring too much, less than E, more than D and A, something like that. You can think like that. Let's do together this analysis. Okay, I want to put there some detail. Let's take the middle right. It can stay good there. Maybe let's take it no, like that. Yep. Yeah, it can stay like that. Have you seen these numbers? That's okay. Then let's start the work. Let's start to encode then decode. We already encode them. Now let's decode them. Okay. Now we have the answers. Let's look for the answers. Now we will say decode the word according to the bit codes in the table in the table. Yep. What is the original 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 word English word represented by that encoding? Amazing. Let's come and solve together. But before that, we'll say A, B, C, D, and E. Let's put there the not space. There, this point. Yep, it is amazing. Our answers will be A will be red raw, not rare. I don't want to manipulate you. Draw, and the other one will be reward. Amazing words. Then we have drawer, right? Then we have order. Then we have word, right? I think word or word. Word. Anyway, later we can look for it. I think word is. Yeah, this is a word, okay? Don't worry about that. Now, let's take pencil. Let's go up. Let's start to solve. But before solve, you can solve it. What it will be. I'm waiting you with the coffee. Oh. Have you solved? I think you solved it. Anytime. So anyway, time to solve it together. If you don't understand, don't worry. Now you will understand. Now it's starting with the 0101. Which is 01? It is that. It is R. It's R. Then we have 100. This one. And 100, it's that. which is 100, is representing A. Let's do it good. Yeah. And then we have 1, 1, 1, 1, 1, 5, 1, which is that I think D is true. This one, let's say this one we can represent with the D. And then what we have 0, 1, 0, 1 again. 0, 1, 0, 1 is again R, which is representing in this point same. It's also recurring less than D and less than V, W I mean. Again, 0, 1, but 1 minute, sorry. This point, 1, 1, 1, right, 0, 1, 0, 1, sorry. My brain is mixed with 10, 10 like that. This is R again. Yeah. R, little beautiful. Yeah. R. Yep. Why is R looking like crazy? R. And then we have 1, 1, 1, 0, which is 1, 1, 1, 0. It is A. Let's look at 1, 1, 1, 0. This point, it will be 1, 1, 1, 0. Let's say this is A. Let's say this is the A. Yep. And the last one, 0, 1, 1, 0. 0, 1, 1, 0. Where is the 0, 1, 1, 0? Oh, sorry. What happened here? I think I forget one thing here. 0, 1, 1, 0. We don't have 0, 1, 1, 0 in this point. The last one is 1, 1, 1, 0, right? Oh, right. 0, 0, 1, 1, 0. This point, it's coming from here. This one is W. I mean, this one. Yep. Yep. So let's come down. What is our solution? Red draw, right? Yep. This is our answer. This one wrong, the wrong, the wrong, the wrong. So we solved it. This is that. You got Hofmann calling. Now you know. What is it? The last one is byte pair encoding. Byte pair encoding is a compression algorithm. Is a compression algorithm is a compression algorithm that replaces repeated pairs of characters in a string with a character that with a character that with a character that isn't in the data and creates a table of replacement mappings pairs put from Dr. Seuss again. Okay, let's write it here. What did you write back there? Think, saying think, think. Left and think right. And think low and think think high. Oh, the the things things you can think. I think this is things or all the things you can think up if only you try. This is some brainstorm. Oh, anyway, thank you, Dr. South, for this amazing philosophic sentences. Let's calm down and let's put anyway it there. Let's calm down and say which of the following character pairs would pairs would the algorithm replace? Would the algorithm algorithm replace? Okay, let's come down. Yep. Now let's say choose two answers here because there is two answer. Say A, B. Let's make in the right B. Yeah, B, C, D. Okay. Now we will examine it together. We will examine it, and consciously we will find solution. We will come up with solution. Let's look at. It's saying which of the following characters pairs would the algorithm replace? The first one. The first one will be what, 2. Second one will be NL. Other one will be in. The last one will be F. Now take a pencil. Let's check it. The first one, do. First one. But 2, I think. Let's don't think about the first one because do is bigger at this point. But let's think about this place. We have 2. This point. We have 2. We have 3. We have 4. We have 5. Yeah. And we have 6, I think. More 1. Where is it? Right. And then here. Yeah, this is replacement is repeating. I mean, this is 6 time repeating. So we can implement this Huffman coding here with the sum bits. Anyway, then we have Enly. Look at the Enly here. Enly is just right here. Enly is right there. Now, what I want to show you in this point, Enly is just recurring. I mean, repeating one time, I will put one here. And in, if you check in, how many in have? We have one, two, three, and then four, and then five, and then six, and then, right, I think six time is recurring, right? Yep, bro. This is this is six. This one is six. And the last one is just recurring one time. FT is like, where is it? Left is like left, and right is the left, I think. Where is it? Right here. It's just recurring one time, okay? The solution here, this, the, and in. We can, so it's saying which of the following characters pairs would the algorithm replace? The D and in. We can implement Huffman coding on of them because this is recurring too many times in the sentences from Dr. Seuss. So anyway, that's all. Thank you so much for joining it. So let's say this one is true, wrong. So not wrong. It's just we can't implement too much Huffman coding. So and then this one is not good. So our solution is A and C. Yes, guys. Thank you so much for joining me to solve these problems together. The next lecture we will speak about lossy data compression. It was finished now here. I would like to see you there again with your coffee if you want to join me. So we will speak about lossy data compression and lossy compression, so you can think like that. Anyway, this is our practice, and we will do also practice about lossy data compression, and we will go other topic, and third quiz will finish, and all the things. Anyway, let's speak later about that. For now, just what I want to tell you is I want to examine with you everything about this process, about computer science, and about all of this stuff. I will share each time this information with you. Just don't worry about that. Just join me and learn with me. Okay, next lecture, we will speak about lossy data compression. Till this time, be careful and have a good time. Thank you so much. See you later.